morning.
Good morning, ma'am.
So let's start quickly. Your first quiz will be perhaps on 2nd February. So before that we have to complete the content of module 1. And the time will be from 6 to 6:30.
Evening.
Yes, yes. All the quizzes timing will be there. From 6 to 6:30, so that there will be no conflicting of timing of classes. Any other subjects quiz has already started?
And 31st.
Ma'am, on 31st we have our chemistry quiz.
Okay. So
how much of content is left in module 1?
Module 1 we have to complete the rectifier, so it will take 2 class, and Zener diode it may take 1 class, so total 3 class we can complete the syllabus. And actually Wednesday is again holiday, so we'll have one more class on Thursday. So Monday we will definitely give one extra class so that we can complete the course by Monday. So Tuesday or Wednesday class we can have some discussion, or we can solve some numericals. Okay, so Monday we will have one extra class. This Monday actually we are having several meetings on the department, so it is not possible to have extra class. So coming Monday definitely we will have one extra class. So I think that same time will be free for you people, like 2:30 to 3:30, na? So on Monday 2:30 to 3:30 we will have one extra class. So by Monday class, or at most time it will require, then Tuesday required. By Tuesday we will complete all the contents.
Ma'am, how many questions in the quiz?
Actually till now question I have not seen, so we have not decided. It may be 20 questions or it may be 10 questions. It will be MCQ type questions only. So maybe 20 questions it can have. A half an hour time is there.
Ma'am, actually our chemistry quiz is going to be conducted within the class time only.
Okay, but in class time is it possible to have all the students have the same time chemistry period on the same time, all branches? Actually the quiz has to be conducted commonly for all the students, like section A to F. All the 6 section students will have the same question, otherwise the uniformity will not be there. So if different quizzes for different section will be conducted in the class time, then there will be variation. It depends upon the teacher, it depends upon the question pattern, like many things is there. So that's why in our department we have said that all the questions will be common to all students, so that uniformity will be maintained.
मैम
Yes.
मैम बाकी सारी क्विज 45 मिनट्स की हो रही हैं, आप मैम 30 मिनट्स की कीजिए।
45 minutes के, whether they are giving the descriptive?
जैसा मैम केमिस्ट्री वाले सर ने भी कहा है और ईवीएस वाले सर ने भी कहा था कि क्विज जो होगी वो 45 मिनट्स की ही होगी।
Okay, so till now we have not having that kind of plan, so I think it will be it is depending upon the teachers.
Okay, ma'am.
Okay, so let's quickly start. So we were discussing about the half wave rectifier circuit. So actually when we discuss about this rectifier, basically it is your DC power supply. We are discussing about the DC power supply. Okay, so this is basically your DC power supply. So as in the previous class we have little bit discussed about the rectifier circuit. From that you can understand that what is the need of rectifier, obviously to convert the AC signal into DC signal. Okay, so in our home or in our office we are having the supply of approximately 230 volt 50 hertz supply. In India we are having 230 volt 50 hertz supply in our home appliances or office appliances. And for industrial purpose this voltage is very high and this is different case there. Okay, so like for other country the rating might be the supply.
Ma'am, please record today's lecture.
Oh sorry, yeah, I'm just forgetting. I think recording has started. Is it visible to you?
Yes, ma'am.
Yes, ma'am.
Okay, so like in India we are having 230 volt AC supply, that is of 50 hertz. Like in different country different type of different ratings are there. Like in US it is about 120 volt supply and 60 hertz their frequency. In many European country it will be from 220 to 240 volts, like that they have the supply. So from country to country it differs how much they are supplying. According to that their appliances are also working. So I think you must have seen that if you are having a laptop or any electronic device which is from US manufacturer or something, their charging pin is different. Have you marked that? So you can identify that what is the difference. So you can have the universal universal adapter or universal chargers are there. So there are different type of pin structures are there. Like just for your example, like this kind of difference you can observe. Okay, so so supply is different from country to country. So whatever the AC supply we are having, as per the requirement of our appliances, we need to transfer into the DC signal. So from AC power line, we need to convert the signal into DC. So first of all, we require a transformer. Okay, transformer for stepping down the supply voltage, and after that transformer we will require one rectifier. So this rectifier will convert the AC signal into your, this is for the step down purpose. Okay, for stepping down, and from that AC signal to this after rectification we are getting the convert from this AC to pulsating DC. Pulsating DC. So here if we are having a very high voltage, then this will be stepped down to the lower voltage, then we are converting this into your pulsating DC, unidirectional. After that you require some filter circuit. We require some filter to convert this pulsating DC signal into a pure DC signal. So after using the filter circuit we will get from pure DC, or it will convert the pulsating DC into pure DC. So after appliances of a filter will have little bit this kind of structure. Okay, so it is almost approaching to DC, but exactly some ripple may be there. And after that we require a voltage regulator circuit. voltage regulator circuit. So this voltage regulator circuit will gives you a constant DC voltage. It will constant DC voltage it will give. So this much steps you require for converting the AC signal into the pure DC form. So in now we will have the discussion of the half wave rectifier circuit. Half wave rectifier circuit.
Ma'am, please explain what is the function of filter.
Filter, we will discuss in detail how the filter will work. Actually, when we are getting the pulsating DC means it is not a pure DC, only we have converted the signal into this alternating signal, that is positive half, negative half, positive half, negative half, this signal into a unidirectional signal. Only in the positive half we are getting the signal, but it is pulsating in nature. Still some AC content is there, still some frequency is there. So to convert this signal into a pure form, it should be DC means the frequency should be 0 na. So the filter circuit will give you that signal. That means we have to use some filter like by using the capacitor or inductor in such a way that it can filter out the AC content and it will pass the DC content. So this will be your filter function. So we will discuss how the filter will work, that we will discuss in detail.
So ma'am, what is the difference between the filter and this voltage regulator?
Actually, voltage regulator means it will here also there may be some fluctuation of voltages there little bit, but AC must be, should be so DC voltage must be a constant voltage, isn't it? It should not fluctuate. So when we use the voltage regulator circuit, it will give you the constant voltage, only a constant voltage. Okay.
Yes, ma'am.
Yeah, so we will discuss about the half wave rectifier circuit. So in half wave rectifier, as we have discussed about in the previous class about this, so we will use one transformer, okay, then one single diode and one load resistor RL, okay, load resistor RL. So here the AC will be provided, okay. Let's say this is the B sin omega t. The alternating current will be represented like this. This is the fundamental representation like V sin omega t. Either you can represent by using the sine signal or you can represent it by the cos signal also. There is no difference. Okay, when we are using the cosine, just taking the waveform from having some little bit phase shift will be there. Okay, so after converting this from this transformer AC input, this AC input will be transformed into this. So here we will get across this we will get some voltage. Let's say this is the input voltage VI. Okay, so this VI will be how much? This is actually this is, let's say, Vm sin omega t. Okay, so what will be this Vm? Vm will depending upon the if you just remind your fundamental knowledge about the transformer, how it is stepping down or stepping off the voltages.
Efficiency of the transformer.
Yeah, so it depends upon the how much winding is there. If number of turns in primary winding is N1 and this is N2, then we can say this Vm will be N2 by N1 into your whatever the supply voltage peak, that is V. Okay, so accordingly whatever the requirement of your voltage, according to you have to decide the winding number of turns present in the transformer. So this transformer part is not much more essential for now. So how much that is from the electrical, when we do the electrical basic electrical part, there we will discuss about this transformer in details. So here our concern is how we are converting this through the diode. That analysis is important here. So now our input voltage is this one, the input AC voltage, which is we are going to converting into the DC signal. Okay, so as we have discussed about this, like suppose this is the applied AC input signal. Okay, so this is your VI, the 0, let's say this is pi, this is 2 pi, this is 3 pi, like that. So this is the signal what is applied to the rectifier. Okay, that is VI is applied here. Okay, so its time period is 2 pi is the time period, so frequency will be how much? 1 by 2 pi will be the frequency. Okay, so for this case, if you find the output voltage, okay, so output, let's say here we are calculating the output, and throughout this discussion we are considering the diode as the ideal one, so there is no consideration of that diode reference, that resistance or that voltage drop across the diode. So we will consider this as an ideal diode and we will derive all parameters. Okay, so what will be the output voltage, like from 0 to pi, as we have already discussed this analysis, how it is forward biased and reverse biased, all this condition. So if you consider 0 to pi, so during 0 to pi we are giving the positive voltage, so this will be, the diode will be replaced by the short circuit equivalent, as it is forward biased during the positive half cycle. For this half cycle the diode is forward biased, and in case of forward biasing of the diode, it will be simply replaced by the short circuit equivalent, and it will be just behaving like this. This is the RL, this is the diode part, and here we have supplied this VI, so this is Vm sin omega t. Okay, so what will be the output voltage? V0 here, so this V0 will be simply your Vi, whatever the Vi we have applied for this part, that will be the output voltage. So that same Vi we are getting here. So here also the peak is Vm, here also the peak is same Vm. Okay, so for the next half cycle, when the signal from pi to 2 pi, the signal will be having the negative half cycle. So for the negative half cycle, the diode will be open circuited. So the diode will be open circuited for the negative half cycle. This is from 0 to pi, and this is from pi to 2 pi, so negative half cycle. So here diode will be open circuited, and in the negative half cycle just the reverse polarity we will use. This is Vi. So there is, the path is not closed, so we are having no current, so the output voltage V0 is also 0 here, it is equal to Vi. So here we are having the waveform like this. So for this half cycle we are getting 0, for this half cycle we are getting again same Vi. So this will be the pulsating DC. This is pulsating DC. Okay, so as so here we can say this this axis will be your omega t axis. This is your omega t axis. Okay, so before connecting the filter circuit, so this is the pulsating DC. So before connecting the filter circuit, let us analyze some parameters when we are discussing about this output. So we will without connecting filter, we will analyze what will be the efficiency of this rectifier, how much DC it is providing. After that, with connection of the filter circuit, we just calculate the efficiency and some parameters of that DC voltage that we will discuss. So some derivations are there, so we will do it. So for this we will derive the AC BDC, VDC, IDC, okay, and like IRMS, VRMS, then ripple factor. Okay, this will be denoted as your gamma symbol. Then efficiency, that will be eta symbol. Then some peak inverse volt, PIV rating of the diode. Then form factor, transformer utilization factor. These are the some parameters which need to be studied when we are discussing about the rectifier. So let us consider one, that is the DC voltage or DC current. Okay, so VDC voltage we need to calculate. So DC voltage means that is the average voltage. So this waveform, whatever we are getting, that is the pulsating DC. So in this waveform, how much DC content or what is the DC voltage, that we need to calculate. So for the calculation of VDC, that is VDC means actually this is the average voltage. Okay, so when we calculate the average, how we calculate the average? for this 0 to 2 pi, this is one complete cycle 0 to 2 pi. So within this 0 to 2 pi, what will be the average of this waveform? That need to be calculated. That will be your DC part. So for calculating this, let us integrate the waveform. So for that particular area, whatever the curve is there, mathematically the calculating the area means integration, taking the integration of that voltage. Okay, so integration of that to your load voltage or output voltage with respect to your omega t, that will be giving you the total area. Then we need to take the average. So take average means 1 by 2 pi we will do. So that will be the giving the average whole value. So this will be 1 by 2 pi. This is 0 to 2 pi, 0 to 2 pi. This output voltage is nothing but your Vm sine omega t into d omega t. So with respect to omega t, we will integrate this. So as we know, from this can be written as this integration can be break into 0 to pi, the same Vm sine omega t d omega t plus again pi to 2 pi, the Vm sine omega t d omega t. Okay, so from pi to 2 pi the value is 0. From pi to 2 pi the value is 0. So for this part we can take this, consider we can 0. Okay, so simply 1 by 2 pi integration 0 to pi Vm sine omega t d omega t. This value will give you the average. So Vm is a constant parameter, so we can take Vm outside, Vm by 2 pi. And what will be the integration of sine omega t? It will be how much? Minus cos omega t. Yes, minus cos omega t. So we will have this minus cos omega t from the value will vary from 0 to pi. So find the value. So this will be Vm by 2 pi, that's a minus sign outside. So it will be cos omega t. So cos pi minus cos 0. So what will be the value? Minus Vm by 2 pi. Cos pi means that is minus 1, cos 0 is 1. So how much? Minus 2, minus minus get plus. So 2 Vm by 2 pi. So it will be Vm by pi. So this will be the DC content or average value of that waveform. Okay, so what is the value of pi? If you calculate, suppose Vm value is 10. Okay, suppose input this AC signal is having 10 sine omega t. So what will be the DC voltage? What is just Vm by pi? So what is the value of pi?
Approximately pi, ma'am, because we assume pi square equal to 10 while solving.
Yeah, so just calculate, suppose Vm is equal to 10 volt. So what will be Vm by pi? If you have calculator, just calculate it and just tell me the result.
Ma'am, it is 3.183.
3.183, ma'am.
Okay, 3.183. So you just imagine it is suppose 10 means 3 point something means almost here we are getting the average value. Okay, almost here we are getting the average value. This is your VDC. Okay, so how much less value you are getting from that half wave rectifier, that is important. Okay, so likewise you can, as you have calculated, this VDC is equal to Vm by pi. Likewise, if you calculate, consider the current signal, that will be also Im by pi. So when we consider current signal, Im sin omega t you have to consider, and just in a similar way you have to take this, and VDC and IDC you can calculate by this one. Okay, this condition here you have not considered any diode resistance or transformer transformer resistance or load resistance. You have not connected anything. Okay, so if you consider the resistance, different resistance part, then in that case it will be little bit different. So in that case you have to consider the current as your Vm by some all the resistance value. Okay, then next parameter we need to calculate, that is your RMS value. Okay, so we will consider the VRMS and IRMS. Okay, so what will be this VRMS, or we can say IRMS, whatever you consider. So if you calculate the root mean square value, what is the significance of RMS value? What is the significance of RMS value?
And that it can be directly substituted for DC formulas by simply applying VRMS in AC signals.
Yeah, actually RMS value or the root mean square value that actually shows the strength of the AC signal. Okay, so how much effective voltage or current is there in that AC signal, that is indicated by the RMS value. Like if you are applying the 6 volt RMS value or 6 volt DC value, both will be having the same value. Okay, so let us calculate the RMS value. So for calculating the root mean square, so obviously we need to root over of mean of square we have to consider. So from 0 to 2 pi, if you take this voltage or the V square we can take, okay, or Vm sine omega t, that value, it's square. Okay, so this will be d omega t and its mean, that means 1 to 2 pi, 1 by 2 pi we have to consider. So for this case let us just solve it and find the RMS value. Okay. So let us just compute it. So it will be root over of 1 by 2 pi. So from 0 to pi we are having the value, pi to 2 pi the value is 0. So I am not writing that steps directly, I am writing it is 0 to pi. I am changing the limit to 0 to pi. So this will be Vm square sine square omega t d omega t. So just do the integration part. Okay, so this will be square root of Vm square by 2 pi 0 to pi sine square omega t. How we will integrate it? We can convert it as 1 minus cos 2 omega t. Yeah, cos 2 omega t by 2 integrate. So this integration we can do d omega t. So just solve this integration. So this will be Vm square by, if you take this 2 outside, this will be 4 pi and it will be integration d omega t 0 to pi minus integration cos 2 omega t d omega t 0 to pi. So this could be Vm square by 4 pi. So this value is d omega t is omega t, so this value is pi minus this will be cos 2 omega t, so its integration will be sine 2 omega t divided by 2 from 0 to pi. So this will be how much? If you take, this is Vm square by 4 pi by pi minus, what is the value? 0 because sine 2 omega t, so sine 2 pi is 0, sine 0 is also 0. So this value is Vm by 2.
Vm by 2.
Vm by 2. So we got this Vrms value, this Vrms value, that is equal to Vm by 2, and similarly Irms value will be Im by 2. This is for the half wave rectifier circuit. Okay. Next, one more parameter we will discuss about this, that is the one more parameter is next is your let's say efficiency. Okay. Efficiency, it is denoted as eta. Okay. Efficiency means always we justify any particular circuit or anything, that's how the output it is providing according to the input, that is the efficiency part. Okay. So for this half wave rectifier, if you calculate the efficiency, what will be the output here? So what will be the DC power supplied to the load divided by the AC power, total input AC power. Okay, total input AC power. These things you need to calculate. So actually this is power, DC power by AC power. So PAC into 100%. This we need to calculate. So here for calculating the DC power, we take DC current IDC square into your load resistance divided by what is your AC power. So it will be IRMS square divided by into I square R. So here the resistance we need to calculate. So whatever the AC signal we are applying, so it is passing through the all the resistance. So resistance value, if you are considering, not neglecting, in that case it will be the diode forward resistance plus the source, the secondary coil resistance plus your load resistance. All this resistance will be considered into 100%. So usually this RF plus RS, these two resistance is very small as comparison to your load resistance. So we can have that approximation also, and we can find. So IDC square, IDC value we have already calculated. What is IDC? That is Im by pi. So this will be your Im by pi square into RL, and RMS is Im by 2 square into that resistance. Okay, this so this RF plus RS plus RL into 100%. So this we can calculate, just simplify it. So it will be how much? This will be 4 RL by Im square get cancel out. So this will be 4 RL square, 4 RL into this will be pi square 4 RL by pi square into all the resistance. So RF plus RS plus RL. So this will be, if you consider this RL is much more greater than your RF plus RS. If you consider this, so this will be RL get cancel out. So simply it will be 4 by pi square. So 4 by pi square into 100%. So it will be, if you are calculating this, it will be 40.6% for half wave rectifier circuit. Okay, so this is the efficiency. So it will be almost less than 50% efficiency we are getting, which is very less. So we will not able to use this half wave rectifier for commercial purpose or for any application purpose. So next parameter.
Ma'am, actually I
Yes.
had it out. Why are we considering RF and RS for only this AC part?
No, not actually. This is AC input power. So input power where we are supplying in the circuit. AC input power means at the beginning we are supplying. Here we are supplying the AC. Okay, so just to show, either you can consider for the other case also you can consider, but only for efficiency I'm just showing you how the resistance is affecting the efficiency. Okay, but that with the resistance you can calculate the other part also. So instead of just to show you the effect of resistance, I have considered here. So if you are not using for the preliminary, then that is also okay. Okay. So if you consider the load, then obviously this resistance part should be known to you, that little resistance is there. Okay, when practically when you do this, you may not get exactly 40.6% of efficiency. Okay, you are having this experiment, so when you do the hardware experiment, in that case exactly 40.6% will not come. So there the effect of resistance is there. So that thing you can calculate in the lab. Okay.
Yes, ma'am.
Okay, so one more parameter is your peak inverse voltage, PIV rating. Okay, peak inverse voltage. Actually, whenever we purchase any diode, its PIV rating is given by the manufacturer. What it indicates, actually this peak inverse voltage is the specification which is given. From that we can have the idea that how much reverse voltage a diode can withstand, okay, without entering into its breakdown region. So what is the maximum limit of that reverse voltage? It can be applied to a particular diode. That information is from that PIV rating we can know. So how to know the PIV rating means in the rectifier circuit, suppose you are using a particular diode. So how much voltage, which diode you have to consider or which diode you need to choose. That information should be known to you. So how do you calculate this PIV rating of the diode? So for that case, as it is the inverse voltage. So inverse voltage means we have to consider the reverse bias condition of the diode. So during the reverse biasing or during for negative half cycle, we can say negative half cycle of the analysis. So in that case, you are having this reverse polarity, negative to positive, your input VI, which is your Vm sin omega t. Okay, that voltage we are applying, and the diode is in the reverse bias mode. That means it is open circuited. Okay, so this is the condition during the reverse biasing of the diode. This is the load P0 we are calculating. Okay, so for this case, I know that there is no current through the load as the circuit is open circuited. So here, what will be the voltage drop across these two terminals, this open terminal? If you measure the voltage, here we have applied a voltage. Okay, here one load is there. So when you measure the voltage, there must be some display of the voltage here. So what will be that voltage if you consider? So the current will flow. Actually, your conventional direction of your current will be how much? From this direction, positive to negative. So this voltage, let's say point, this is A point, this is point B. So within this point, what will be the voltage difference VAB that we need to calculate? Okay. So what will be the voltage if you calculate? Here the output voltage, there is no voltage drop across this output. Okay. So what will be the voltage here? So obviously this is BM minus BM voltage. In this terminal, maximum voltage is your VI, where BM we are applying the peak voltage. Okay. This terminal it is connected to this terminal only. So if you calculate measure, suppose you put the voltmeter here. So there is a closed circuit now. So obviously there must be some display of your voltage here. So what will be the voltage?
0.
Is it 0? Voltage drop is 0. BM.
That's the peak, like
yes.
It will change with time.
Yes.
It will change with time to VI.
Yeah, that so the
V0 plus VI.
This voltage is your peak inverse voltage. So what is the maximum voltage it can display? That is the BM amount. So this PIV rating is BM. Peak inverse voltage, that means maximum voltage that will be appear across this open terminal is BM. So you must reverse voltage. I'm asking about the reverse voltage. So when you choose a diode, obviously its PIV rating must be greater than this BM should. You should choose the diode whose PIV rating is greater than equal to BM. Then only the circuit will be safely operated. Okay. Actually, maximum reverse voltage across this terminal is VM. So when you choose a diode, its PIV rating must be greater than BM. When you choose a diode for this particular designing the half-wave rectifier circuit, its PIV rating must be greater than BM. So peak inverse voltage means it is the maximum reverse voltage that a diode can withstand. Okay, so when we calculate it for the other rectifier, that is like other full wave rectifier, this PIV rating may be different. So based on this PIV rating also you can compare the circuits. Means if you are having a higher PIV rating or this PIV rating requirement of PIV rating is more, in that case that can be also a characteristics. In like suppose when we discuss about the full wave rectifier circuit, that is the which one, that is this center tap rectifier, there will get the PIV rating twice of VM. So center tap rectifier, it is having a higher PIV rating diode. So the diode, when the diode will be manufactured, it should be in such a way that it should be manufactured so that it can tolerate more reverse voltage. So that is also one point which can be considered as the difficulty of that particular circuit. Okay, so this is the PIV rating. Then next part is one more factor is that is called the your form factor. Okay, so simply if you take the VRMS ratio of your form factor, so this form factor, based on this parameters, some numerical may be asked from the quiz questions. Okay, so form factor is a parameter which is just denoting the ratio of your RMS and DC value. So VRMS by VDC, or we can say IRMS by IDC. This ratio is called as your form factor. So if you calculate the IRMS by IDC, this is IRMS is IM by 2, IDC is IM by pi. So this value will be pi by 2, so it is 1.51 for half-wave rectifier circuit. Then one more important parameter is your ripple factor. Ripple factor. So ripple factor is usually denoted as gamma sign. So this ripple factor, actually this ripple factor means how much AC content is there, like in the waveform, in like pulsating DC waveform, whatever we are getting at the output. This pulsating DC waveform, when it is having, it is not a pure DC as we know. So when you calculate the DC, just 1/3 of this we are getting up the maximum value as the DC voltage. So obviously this content some DC part as well as some AC part. So we have to identify that how much AC content is there in this waveform. That will be denoted by the ripple factor of your rectifier. So which is a very important parameter. So any waveform, if you consider any output voltage of this rectifier or this load voltage, you can consider. And there is a mathematical tool, if you have heard that name, that is called the Fourier series. Okay, so have you heard the name Fourier series?
Yes, ma'am.
Yeah. So what is that Fourier series?
Ma'am, in that we can convert any in a standard equation into a series, in a standard signal into a series of into an infinite sum of sines and cosines.
Yes, yes. So if you can represent any signal, any periodic signal into the sine and cosine term. Okay. So there is a formula of your Fourier series. So according to that, suppose the load voltage, it can be represented by the Fourier series. So it will be having some Bm by pi plus Bm by 2 sine omega t minus twice Bm by pi into summation of your cos 2k omega t divided by 2k plus 1 into 2k minus 1. This is the formula of your Fourier series. So it will be k is equal to 1 to infinite. So it will be having infinite number of terms. So there is no need to consider all these terms. So only you just identify that there is no, in the first term there is no sine or cosine term is there. That means it is a fixed quantity. Bm is a fixed quantity, pi is a fixed quantity. So this represents your DC part, and rest of the part is your AC part. Okay, so whatever the pulsating DC signal we are having, if you just this is also a periodic signal, it is having a period of this 2 pi. So this periodic signal can also be represented or in the fraction of AC and DC part. So this content some AC, although it is the, we are considering this as a pulsating DC, or we can say this is the having some AC content or DC content, DC part, but still it is having some DC content. So we can represent the RMS value, that is RMS value when we are considering this BRMS. So this is the effectiveness of this signal we are considering. So this BRMS square, that is considered as the VDC square plus, let's say, BRRMS. RMS square. So this BRRMS is actually mean to this part, this AC content of the signal. When we only represent the RMS, BRMS, that is the BM by 2 we are representing. So that RMS is just the effectiveness of this signal. So here just we have segregated this into DC part and AC part. And for this AC part, if you represent the RMS value, just let's say this is BRRMS. So this BRRMS is the RMS value of the AC component. So for this ripple factor is the measure of your, basically it is the how the successfully your rectifier is converting the DC into AC. That successfulness is represented by this ripple factor. So this ripple factor is denoted as this gamma is equal to this RMS value of the AC component divided by the DC component. So that is mathematically your BRRMS divided by your VDC. So let us derive this, how much this value will be. So as we know, this BRRMS square, that will be VRMS square divided minus VDC square. So BRMS value is known to you, and VDC is also known to you. So we can have this BRRMS square by VDC square. Some mathematical just adjustment we have done. So this will be BRMS square by VDC square minus 1. So just put this as this is BRRMS by VDC, that is equal to square root of this part. So BRMS value is your BM by 2. So this square minus VDC is VM by pi, this square minus 1. So if you just compute this, it will be pi square by 4 minus 1 root over. So this value will be how much it will be, just compute it, it will come to 1.21. So this will be the ripple factor of half-wave rectifier circuit. So as ripple factor is as much smaller, that is good efficiency will be more. So for the half-wave rectifier circuit, usually we got 1.21. When we calculate it for the full-wave rectifier circuit, it will come across 0.48. So this ripple factor is 1.21 for half-wave rectifier circuit. Okay, so these are some parameters. I think one more parameter, that is the transformer utilization factor and your voltage regulation. These two parameters are left. So in the next class we will derive these two parameters. After that we switch over towards the full wave rectifier circuit.
Excuse me, ma'am.
Yes.
I'm going to scroll over just once. To the like the Fourier series transformation ones.
Yeah.
Yes, just a second.
I'm just sharing this this file. Huh? I will share this.
Okay, ma'am.
Okay, you can go through it.
Okay, ma'am. Thank you.
I think it is your next class time is already. So just wait and just let me download the attendance